Today, we are standing at the intersection of two of the most exciting fields in modern science. One of them is quantum computing, and the second one is artificial intelligence. On one side, we have AI, which is hungry for more data, more computing powers, and all. On the other side, we have quantum computing, which processes informations that classical computers simply cannot. But the question is, what if we can combine these two ideas? So will they work together, or will they eat each other, or so how this thing will work? So in the next 1 hour, we are going to find out exactly how they are starting to blend. So here is our roadmap for this session. We'll start with the fundamental shift from classical bits to quantum qubits. Then we'll see the relationship between quantum computing and the AI in two different directions. One is how AI can help, how AI can solve the quantum hardware related problems, fix the massive errors that arises in quantum computers. And the second one is how quantum computing can solve the problems related to AI. So how quantum for AI will be helpful. so, so finally, we'll cut through the hype versus reality and look at where the real opportunities lie for the researchers today. And we'll see the applications and research opportunities in this area. So the first question comes, why quantum AI? So, so why not just stick to NVIDIA GPUs? So let's begin with the history of AI. So 1950s, so Alan Turing's question like, can machines think like humans? So it started from there. Then 1956, this AI, artificial intelligence, this term was coined. 1986, backpropagation, which helped for computation. Then in AlexNet, the use of GPUs powered deep learning related works. Then in 2022, the ChatGPT came, and this became a household name. This AI became a household name. But now we are in 2026. So what will be the next breakthrough? So is it agentic AI that is happening, or maybe people are saying that is artificial general intelligence (AGI), or maybe physical AI? So how this AI is being used, robotics, automation, those things are coming in, or maybe the quantum AI. So this is the, we don't know where we'll go from this place. But so the thing is that in the reality of modern AI, we are dealing with billions of. I'll just discuss why we are coming to why we are looking at quantum AI. So we are dealing with billions of parameters. Training GPT-4 cost hundreds of millions of dollars in GPU infrastructure and energy, and it took months. So it is getting prohibitively expensive. So classical computing is hitting a physical wall that is that kind of shrinking. The transistors are now becoming as the size of atoms. So we need fundamentally different way to compute, not just a faster one. So now from CPU to GPU, now something like NPU is coming. So that is where we are turning into quantum realm. Let's see how this quantum can help for the better of these AI related things. So I know the audience, most of the audience are familiar with quantum qubits and so, but I'll just for the sake of completeness quickly go through the basics of quantum computing. Then we'll get into how this quantum and AIs are interacting. So first we'll start with the qubits. To understand the quantum AI, we need to understand the basic tool. So that is this qubit. Sorry. So a classical qubit is like a flip coin, which is either head or tail. But qubit is like something where it's flipping. So in the real, if you look at the flipping coin, so which has a probability of coming as both head or tail, both at the same time. So that can be either head or tail, right? So we call this situation as a superposition. So you people know better than quantum computing than me. Many of you may feel boring, or if there are some mistakes I am saying, please point out, because I am also learning this quantum computing and AI is my field mostly. I am trying to use this quantum circuits and so on my AI related things. So please stop me if I'm, or please correct me if I'm doing something, if I'm saying something wrong, because I know this platform has many experts in related to quantum. So so when we're talking about superposition, so this doesn't just double the information, as I'm saying, probability of head and tail, but this kind of this makes exponentially this scales. Okay, so now next we'll see, as we have discussed about superposition, but superposition is not enough. So we need qubits to interact among themselves, and they do this through the technique that is called entanglement. So most there are many examples, but imagine, let's say I am putting a pair of globes into two boxes. I send one to you, and I have one with me. So if you open your box and found that, so it is the left hand globe. So instantly you know that my side has a right hand globe, even though we are miles apart. Right? Entanglement is that spooky connection, as Einstein used to call this. So when two qubits are entangled, they act as a single system. So without you cannot describe one without describing the other. Right? So as it is written here, psi of AB is not equal to psi of A. Take this product with psi of B. So that means we cannot directly write one as a product of two subcomponents or sub qubits. So it means they are inseparable. So this is the secret ingredient that allows quantum computers to outperform the classical ones in some task, or maybe in specific tasks. So better to say. So next, the idea is the quantum measure. So to get an answer out of a quantum computer, you have to measure the qubit. But the act of measuring it is like shining a bright flashlight on a cycle. The moment you do it, the qubit collapses from its magical superposition state into a boring classical state. So either it's 0 or 1. So once you measure, so it destroys the quantum magic. So for example, let's say it is in the superposition or so. So if you measure, then it comes to the classical state 0 or 1, depending on how much probability so this state will take. Then we'll discuss the quantum gates. So quantum gates are nothing but, so these are some operations, unitary operations, unitary linear transformations on each of these qubits. So once we have these qubits, so how do we manipulate them? So these quantum gates comes as the operations, or maybe you can think of these quantum gates as the operations on each qubit. So we do this physically using we blast with microwave pulses or lasers. So some gates like the Hadamard gate, so they create superpositions. They take, for example, the 0 gate and make it blurry. So other gates like C0, they entangle two qubits. Then some gates just flip the states and so on. There are many. I don't know exactly how many number of gates are there, but there are many gates. So mostly they help to change from one qubit to another qubit. So they can, so as I have written here in three points, so they can take one indefinite state and turn it into superposition, or they can take a separate qubit and entangle them, or they can flip the qubits state. Okay, so these are the these are the outputs that we get from the quantum gates. Then let us look. I've just given one example. So if I'll share this, maybe later somebody can check what do you mean by quantum circuit. So I'll come back to this quantum circuit also later. So here I have taken one quantum circuit with 0 and 1. So this X gate and Hadamard gate is applied, then C0 gate, swap gate, and what is the final output is coming. Just for the example I have taken here, but I think better we can skip this. So now let's come back to the main part of our talk. So the relation between quantum and AI. So this is two-way, as we are discussing. First, AI for quantum, where we'll use classical ML and DL, classical machine learning and DL, to correct the quantum hardware. The second is, so we'll use quantum computers to help AI to work better. So let's take them one at a time, starting with the AI for the quantum. So the first one is AI for the quantum, where we'll see these things like how can you do error correction, noise prediction, or quantum circuit optimization. Then when we'll come to the quantum for AI, then I'll discuss two methodologies there. One is pure quantum ML, and the second one is the hybrid quantum ML. Okay, so so I have taken these three examples that we have discussed, that we are going to discuss: error correction, noise prediction, and quantum circuit optimization. So, in real quantum hardwares are noisy. So the qubits decohere in microseconds. So one of the most active applications of AI is we use this AI as a decoder. So spotting the error pattern and telling the hardware how to correct in real time. So this is the so instead of classical methods, so there are some classical methods. So to do these error corrections, but we are training the AI model. We are showing some existing errors and so existing noises. So from that, so they predict. So how does the error look like? So it's not only about predicting the error or predicting the noise where it is. It can help, the AI can come in to help to reduce the noise also. Okay. So using models like sequential models like LSTMs or graph neural networks, so this can be trained on the historic gate error and coherence data. So the hardware can proactively settle around bad qubits, so it can predict the errors before it happens. Then the third application that we are going to see, the where we can use AI, is quantum circuit optimization. So it does not simply deal with noises or errors; it can also redesign the circuit itself. So there is an idea called reinforcement learning, where agents try to learn by themselves, try to correct by themselves. So an agents can redesign the circuit with lower error and shorter depth. So these things. So these are the just three applications, but there are of course many applications of how we can use AI to for the quantum computation part. Now that we have seen is quantum AI for the quantum side. Now let's switch the lens to talk about the quantum for AI. So I'll just quickly remind how this standard machine learning or the deep learning pipeline work. So we have some data, then we initiate some parameters, we train some, let's say we train a neural network, then we evaluate the model. If the model is working good, then we deploy the model, or then maybe we use the model for to doing the prediction and so. But if the model is not working good, so if there is much error, then we update the parameter. So this is basically the training phase. Then again we evaluate if the training is error is less. So our goal is always to reduce the training error. So what happens? So how do we insert, or how do we bring quantum computing or quantum circuit into the picture? So let's recall what we have discussed before, the quantum circuit. Quantum circuit, as we have discussed before, so it's simply a sequence of quantum gates. So we apply each gate one by one to the qubits, and it transforms from the initial quantum state to the final state. So, but now we'll think of something which is called variational quantum circuit. So variational quantum circuit is something where instead of simply fixing all the for example the parameters of a circuit, let's say we have a rotation gate. So instead of fixing the rotation angle, if you'll say let that rotation angle theta is a parameter. So the same circuit for different angles can produce different outputs. We'll use gradient descent, or maybe so not exactly the gradient descent for the quantum, but something like this, the parameter shift rule, or maybe there are some methods also for gradient free guessing, so that we can use to update the parameters. So this is not only that rotation angles are the parameters in the variational quantum circuits. So for example, let's say which gates to use. So there are different type of gates. So which gates to use, then which qubits to connect. Maybe let's say first qubit or second qubit, or second qubit or third qubit. Where to place? Where can I place the gate? So these are the operations, or these are the things that we can ask in the variational quantum circuit as the parameters. Also there is something called quantum architecture search, reinforcement learning. So these things we can implement to design the circuit in a better way. So what I mean to say here, so not only the thetas or the angles that will work is the parameters, but there are many other things like to place the, where can we place, so which gates to connect, which gets to entangle. So these things can also work as parameters in a variational quantum circuit. So what happens here? If we'll see, the data is going, and in the training phase we have a neural network, but in the quantum phase, so what will take? So I have divided the quantum phase first into two ways. One is called the pure quantum machine learning, and the second one is the hybrid quantum machine learning. So hybrid classical quantum, it should be told hybrid classical and quantum machine learning. So in the pure case, what we will see. So in the input data, so it goes then completely the computation and everything. So this has been done in the quantum computers, quantum encoding, then quantum circuit. So as we have discussed about the variational quantum circuits, so they work like as a replacement of the neural networks. They, sorry. Then the outputs are measured. Then we do some prediction if it is correct or wrong. So accordingly we update the parameters and so on. So this is simply pure quantum. So we are replacing the neural networks with a quantum circuit. But in case of the hybrid quantum machine learning, so we have the data. We use this classical feature extractor or maybe the classical neural network. Along with that, we also use this quantum circuit. So both the classical and the quantum, both of them are present. Sorry. Then we say this is hybrid, classical and quantum machine learning part. So we can want a better for better visualization purpose. So we see in the classical architecture, in simple classical, so we have some input data, we have this neural network, and the so all these things are output. I have written it input by mistake. So this input data is going through some simple neural network. The weights and the biases, they are so they are initialized. Then we during the training process we update to get the less error, so on. So this is the classical architecture. But in the case of pure, so we replace this replace this neural network with a parameterized quantum circuit. But in case of quantum and classical hybrid architecture, we have both. So we have these quantum circuits, we have these neural networks. So maybe the classical neural networks work, for example, let's say we have an image, the classical neural network will work as a feature extractor. Then whatever the features are extracted, on that we can apply the quantum circuit. So this is the basic difference between classical pure sorry the pure quantum and the classical quantum hybrid architecture. So this is the one of the kind of best work I have seen in Nature Communication. I think this paper has been published by Kong et al. So what they have done. So they have tried to. So this is an example of the pure quantum CNN. So what they have done. So instead of taking convolutions and pooling, so the convolutions and pooling mostly we use in convolutional neural network, which is used for image classification. So they have used unitary operations, unitary matrices or unitary gates. So as a convolution, so and so so basically they replaced the convolutions with quantum gates, and they replaced with the pooling with all the also the quantum gates. So seeing by which qubits are important. So to keeping those qubits. So pooling is basically to reduce the number of number of so what should I say, input variables. So by calculating the qubit importance score and so on, so they reduced the number of qubits using these quantum circuits. So this is I think this one is published in 2019, where simply they try to do like a normal CNN. Instead of normal CNN, they have used quantum circuits for the convolution operations, for the pooling operations, and so on. So here I will show. So this work is my work. So we have recently, so as I was telling, recently we have started this kind of things. So we are using quantum circuits along with the hybrid, along with the classical networks. So we have done this for Alzheimer disease classification. We have these brain MRI images. Then we have used some feature extractors. So feature extractors basically simply like that, because it's an image, so there are many pixels. So it tries to reduce the picture number of features. So using MobileNet V2, we have used in the architecture MobileNet V2. Then we have extracted the features. We have flattened it to 1280 layers. So from 1200, sorry, by mistake again. So this should be something like 1024. So I have kept here 1280. So we have reduced this to 1024 features. Then again in the classical network, we have tried to use classical network to reduce this to 10 to 24 1024 features to 8. And also this quantum network we have used from 10 to 1024 to 8. Then these features, whatever the features are coming out, we have concatenation. Then there is a fully connected layer, again a classical layer, so which you tries to predict if it is Alzheimer or not Alzheimer. So this one is submitted in a this one is this work is submitted in a journal. So simply, so what happens in quantum CNN and classical CNN, the pixels we use these encoding methods, we convert them to qubits. The convolution filters. So basically, this is a comparison between the last two figures that we have seen, or maybe so not the last two figures. So better to say maybe this is the comparison between the classical CNN and the first figure that we have seen here, the pure quantum CNN example. So the pixels are converted to qubits using encoding methods, the quantum encoding method, the convolution filters. So in that paper particularly, so there are these parameterized unitary matrices are used. Then the pooling, this measurement and qubit. So whatever the according to the qubit importance codes, then the we discard the qubits. Then instead of softmax, so they have used this quantum measurement for finding the expectation values to the final qubit. So the now the most important question. So whatever so these are some of the applications. Of course there are many applications, so and so, but so is this really going to help, or this is simply a hype? So as the figure I have tried to put here, so quantum AI, so it's saying that quantum AI will replace the classical AI. This is not completely true. So quantum AI will complement the classical AI. Again, we are in 2026. I do not know what will happen in the future. So research is going on and so on. So I'm just trying to predict what is the situation right now. So quantum AI combined with the classical AI. So this is giving better results because purely quantum. So this is not easily available to run because we need quantum computers and so on. Computationally, this is not possible right now. But yes, so what is most of the people that they're doing is hybrid this quantum and classical one. So quantum AI is faster. So this is not also true because quantum AI mostly we are running now in classical computers. So this can be faster in specific problems, but this is not faster always. Quantum AI solves everything. We also cannot say like that. In some cases, some examples, we have seen that. So this quantum AI is performing better than the classical AI, or maybe better to say hybrid quantum classical is performing better than the classical AI. The quantum AI has potential, so we think this is the kind of time where quantum AI will grow. So both of them will complement each other. The research is going on. So hybrid models are showing good promise and so on. So there are many applications of quantum AI wherever. So we have this optimization, simulation related things where we can apply AI. So there also we can try to use a quantum circuit idea to see if this can better the performance of the AI models. Then so we are in a phase because quantum AI is growing. So there are many open research opportunities. So if there are some AI people or the computer science people, so we can explore this quantum deep learning, quantum computer vision, quantum NLP, reinforcement learning, and quantum explainable AI, quantum federated learning. So wherever basically we are using or AI is performing well, so there we can try and see how this quantum part will contribute. And the second, for the quantum computer people or the quantum computing people, so how these better quantum algorithms, error mitigation, quantum networking, quantum optimization, or scalable quantum hardware and fault tolerance quantum computing. So this can how this can be done. So this can be explored using AI. How this can be done. So as requested by Professor Panigrahi during the last talk, so he wanted to show me one hand kind of one hands-on where we have done this code. So I'll just show you. So I'll come back to this slide later. So let's see this one. Okay, so basically this is kind of one of the codes that we have. I have shown you to the students how basically this is working. So I'll just show you that. So here simply we have started with this Alzheimer dataset that we are talking about. So then we have used quantum. I'll just show you the quantum part. Sorry, I had throat infection in such a bad way. Yes, so we have used Pennylen for doing this computation. So mostly I'll just show you. So we have this X is basically the image and Y is if the person has Alzheimer or not. So then, so here we have taken this quantum circuit, then quantum angle embedding in the circuit and strong entanglement. So as you can see, here we have taken weights equal to 3, n qubits. My n qubit is 4, total I have taken 4 qubits here. Then 3 is equal to, this starts for 3 layers. So what happens here, total, if you just multiply 3 kind of 3 layers, then 4 qubits, 3 into 4, 12, and the parameters in a strong entanglement layer. So there will be 3 parameters. So we have the rotation with respect to x, rotation with respect to y and z. So these parameters are theta 1, theta 2, theta 3. So 3 parameters, then 3 into this n qubits is 4, 3, 4, 12 into 3, total 36 number of weights. But when we are taking CNN, so mostly we have thousands of weights. But if we are just dealing with quantum circuit, of course, in this model we have taken hybrid classical and quantum. So where we have this CNN and we have this quantum, but mostly if you just look at only the quantum circuit, it has 36 number of weights, where the CNN or the classical convolution dot network that will have at least thousand number of weights. So then we have used this quantum circuit, as I was telling, as a parameterized quantum circuit, where these angles in the strong entanglement, these rotation angles will work as the parameters and will optimize using so that things are written in the code. So I'll just I'll share the notebook also later if you want, anybody wants, you can check it out. So this is the circuit that we have used. So in the Pennylen basically, so by default they take the rotation with respect to y. Of course we can take with respect to rotation x and z also. So here, as I was telling about, so so we are taking 3 layers. I have just shown you one layer. We are rotating with respect to x, y, and z, the each qubit. So this is a strong entanglement kind of in the Pennylen. So you have 3 parameters and 4 qubits, 12 and total 3 layers. So total 36 parameters are coming from here. Okay. So yes. So I'll just maybe going to stop in 1 or 2 slide. But yes. So now, so the question that I want to ask, so really, are we in the phase where this quantum and AI is really working good, or we are just in the hype that kind of quantum AI is, what is the reality of this? So if this is not true, so I'll just kind of give a closing thought. If quantum AI has not yet demonstrated clearly commercial advantage, why are companies like IBM, Google, and Microsoft investing billions of dollars in it? It seems like a massive gamble for them, right? So history teaches us lessons. In 1950s, classical classical computers filled entire rooms, cost millions of dollars, but only they were able to solve simply like calculations that the calculators used to do, right? So if you had told those engineers in the 1950s that one day the computers would sit in your pocket, in your mobile, and do the task like the AI is 3 million parameter, 3 billion parameter, this ChatGPT is doing, so they would have called you a science fiction writer. But now, so we are in the same stage for quantum AI. The first AI revolution happened because we got better algorithms. The second revolution happened because we got GPUs and massive data sets. And I believe the next revolution will happen because we build better computers. And the quantum is the next logical step. We are planting the seeds today for the AI of tomorrow. So this is, I'll just stop. I think I have taken only 30 minutes or so. But yes, if you have any questions, anyone interested in something, some part, please tell. And if maybe I would have been wrong at some part, please correct me wherever you want. Yes.
I have two questions. So,
Yes.
thank you for a very uh, interesting and informative talk. How do you verify output or or validate output results? Do you have any checks which you usually perform to validate them?
So to validate mean, so for example, let's say you are talking about how much the accuracy of the models are coming. So this kind of things you are asking, or
Yes, this is the first one, and the second one is, I mean, this is related with the stability of your approach. And the second, I mean, let me clarify my thoughts. So, if the dynamics is unitary, then we can check whether energy is saved or not, or we can check density metric properties. In your case, do you have similar checks? If yes, then what are they?
okay. So let me first answer the first question that you asked. So how do we, for example, let's say ki, now we have this hybrid classical quantum or the code that I was showing you. So it simply, if I'll take this quantum circuit with angle embedding and strong entanglements, so this is not performing well. So the kind of the results that we are getting. So if we talk about class simple CNN, convolutional neural network with 3 layers or 4 layers, so this outperforms this quantum hybrid classical quantum network. But if I'll try to introduce different entanglements or maybe different embedding methods here, so we have seen that the results are coming good. So for example, let's say there is something like icing scattered. So those, using those things, using multiple layers, using more number of qubits, so we have seen that the performance is coming better compared to the classical ones, the classical and quantum combined, I'm saying. Does this answer the first one?
Yes.
And about the second question that you said, so it's completely the unitary matrices in the proposed in the work that I have shown here. So this is completely by the this image I have also taken from his paper. So this Kong and the other authors that published in 2019. So they have used this method, but I'm not saying this is the only way. So this is the way so that they have proposed, and this is the way that they have used and got good results. So this is one of the breakthrough work of this quantum AI related thing. So where these quantum circuits are fast, or very fast, or maybe popularly used as the replacement of neural networks. So maybe there are different methods or different matrices which can be used, and I think quantum people can better answer these kind of things. So why, or maybe which we computer science people can experiment and see, but why these unitary matrices and all. So maybe I'll leave, if there is some expert in the audience, maybe if they can come in and discuss this.
Thank you. Could you show the references used by you?
Yes,
I
yes,
mean, I
yes,
can see the figures 6 and so on.
yes, yes. The paper 6, I would say.
Yes, yes. So, could you go to the previous slide? I mean, number 27, so that I can also see the references. Okay, and 29, please.
29, we don't have any
Ah, yes,
references.
okay,
Yes.
nothing. Thank you.
Yeah, Ashish, am I audible?
Yes, yes.
Yeah. So, good evening and thank you for a very basic lecture. So, can I get your email ID? I want to get in touch with you for some of the purposes.
Yes. I'll just put it in the chat box.
Chat box. Okay, so let me check. Chat box.
So I will love to kind of take help from you people, because so this is the platform. So what thank I will thank to Professor Panigrai sir for giving this opportunity, because I wanted to connect to the quantum people, because we do the quantum computing like what the example that I have shown you. So this is one of the work, but there are 2-3 works that where we are trying to use the quantum circuits, but we are just doing the experiments. So we do not really understand the so why, and that maybe one of the person, I just forget the name, who asked. So as he asked why, or maybe how quantum is coming into the help, or maybe what particular quantum, without doing the experiment, how can you say that this gate will work better here, or this gate will work better here, there. So this is the thing where maybe quantum people can come and help. So I would love to connect if somebody someone will be interested.
Yeah, definitely. So actually, so you are from mathematics background, yeah?
Right. So I
Yeah.
have
So
done
I
the
am from
PhD in
physics
mathematics.
background. So I will talk to you later, maybe through mail.
Okay.
Thank you.
Ashish, I
Thank you
have
for providing the email ID.
Ashish, I have a question for you.
Yes, you are not audible. Can you be a little louder?
Ashish, am I audible?
Yes.
Ashish, very nice talk. And see, you said that in pooling, that level of pooling, you are doing dimensional reduction. Are you using some SVD kind of thing, quantum SVD?
Sir, to be honest, I haven't exactly gone through that paper, but
Hmm.
yes. So for our paper, I can say you dimensionality reduction. So there are many kind of classical methods.
Hmm.
So I this is something, let's say in the classical case using PCA, so that we
Hmm.
can directly reduce, or even putting a neural network, so that will also
Hmm.
help to reduce the dimension. Let's say we have 1024 or 1000 number of features, so just I
Hmm.
can put a complete or dense neural network of 1004, so that will
Hmm.
reduce the dimension to 4. So the neural network will handle, so how to reduce, or how to maybe what is the parameter, how they are reducing,
Hmm.
so that can learn by itself, and that can do. Because as you have asked this question, I will tell from my experience. So we are trying another work. We have tried to see the principal component analysis. There is a classical technique,
Okay.
so to
Okay.
reduce the dimensionality. So that didn't work, but a complete neural network, simple neural network, that worked better. So maybe
Okay.
the quantum SBD can also be used to see if the to reduce the dimension also. So if that will work or better. So that is the uh, thing, or maybe that is a output that I expect we will discuss.
Okay. So just one question. I'm just
Yes, sir.
curious to see what kind of output we got. You applied it some brain image, right? Can you just go
Uh,
back and show?
yes, sir.
I'm just curious to see that in
Okay.
hybrid,
Okay.
how good
So
we are
I'll
in.
show you. Yes.
Uh,
So I will show you the classical result. This gave us
yeah,
93% accuracy.
right.
So, but if, when we have tried with the hybrid, so this is the simplest one. I have kept
Right.
only the simplest one just for the showing for the simplification purpose. So I get
Okay.
here 77%. But
Acha.
what we have done in that work, so that the
Hmm.
paper that I'm saying, so we
Hmm.
kind of changed it. So we have taken this hybrid quantum circuit in a different way. So by
Hmm.
combining the classical and the quantum in different ways. Also, we have increased the quantum qubit sizes, then
Hmm.
number of qubits, then the depth of the kind of quantum circuit, and so. So then
Okay.
ultimately we arrived higher accuracy than this classical one. So
So
our
that
final
okay.
accuracy was almost like 95%.
Yes. No, that is believable because if you see our Gyanaranjan Sahu here, he
Yes,
was
yes.
trying the similar kind of thing. He claims that finally quantum, he was of course using this on-surf measurement and those kind of techniques for
Okay.
measurement. But we can discuss. It's very nice actually. I have just one more question. Is it
Yes,
okay? I have
yes,
just
sir.
one
Yes.
more question. Uh, see, point is this. See, do you have, when you do this kind of AI and things like that, machine learning, you know very well that the thing that helps is this fixed point theorems, like, Markov's fixed point theorem, those
Right,
kind
right,
of things.
right.
Now, are there analogous things for quantum?
Ooh, I don't know, sir, but I'll
Hmm.
try to see. I'll try to
Hmm.
explore that. Yes.
Because if you remember that, Professor Murthy,
Yes,
used to
yes.
always emphasize on these theorems, which play a very big role in this, getting down to the ground state and things like that, right? And so I was just because see now it may not be there because they are all dependent on this that network kind of structure. This quantum network kind of is coming to existence now. You can check out people like Asin and others. So there are slight differences in case of quantum network versus classical network. Maybe those kind of theorems for quantum domain may not exist or maybe existing. One could check out if those kind of things there, like random walk, quantum random walk is quite different from classical ones. So if you get come across some of those kind of theorems, you would like to learn.
Yes, yes,
We
sure.
can discuss about that. Yeah, thank you.